today we're talking about something called a sampling distribution. Okay, sampling distributions are like, the easiest way to describe it is, I have kind of a little bin here. You guys can look at this bin, right? Imagine this bin is like, each bead in this bin is a person, right? Okay, so if I'm taking a sample, I'm going to randomly go in, randomly select my sample of people, so you guys can kind of get a vibe for this. Sam's got a good vibe on it, yeah. Okay, and as you look at this, we can see that this sample has 1, 2, 3, 4, 5 yellow beads in it. Is everybody good? If I put this sample back and take another random sample, is it also going to have 5 yellow beads in it?
Probably not.
6. You guys see what I'm saying here? What if I do this again? Oh, a lot more than 6, right? Looks like 8. And again. And every time I take a sample, the samples aren't all going to match each other. Okay, so sampling distributions are like, well, couldn't we have taken that sample and written down 6 yellows, and then 8 yellows, and then 8 yellows, and then 7 yellows, and so on and so forth. So take a sample, measure something from that sample, and then as soon as I measure that sample over and over again, I have a new set of data. That is the measurements from the sample. Is everybody good? Okay, we're going to focus on what happens when what we measure from our sample is the mean. Is everybody good? So, we're going to start with a very, very simple population of 2, 2, 5, 5, 9, 9. So, we're randomly selecting, we're going to draw a histogram. What's the frequency in our population for the observation 2? How often does a 2 happen? Twice. And then for 5?
Twice.
9. Twice. Lovely. Great. And y'all, when you're looking at those, if I asked you to describe the shape of this, do you guys see how it's flat? It's uniform. Uniformly distributed. Could we find the mean of our mean and standard deviation of our population? How do I find the mean and the standard deviation of my population? Throw these into L1 and run the one variable stats. So can you guys throw those into L1 and run the one variable stats for me, please?
Yeah.
5.3 repeating, right? And then what was the standard deviation?
2.87.
Did you use the sigma or the S? Because this is a population, so we would use sigma.
Sigma's an OX thing, right?
Yep.
Yeah, I use sigma.
So 2.87?
Yeah.
Are we all in agreement on this? All right, you guys. So now let's imagine I'm taking these numbers, writing each of them on a note card, crumpling it up, throwing it in a hat, and I'm drawing names out of that hat. Is everybody with me? Or drawing these numbers out of a hat. I'm going to draw 3 of them. What's one possible way I could draw 3 of these numbers?
2, 5, and 9.
One possible way is 2, 5, 9. That's one possible sample. How many ways could I draw 2, 5, and 9? You guys get the question? Because, like, I could draw 2, 5, 9. I could draw 2, 5, 9. I could draw 2. You guys catch my drift here? So, how many ways could that happen?
Probably thousands.
So let's see. Kind of would look like this, right? I'm going to call this 2A and 2B. Is everybody with me? And then, so if I have 2A, I could have then 5A, 5B. Does this help to kind of visualize it? And then 9A, 9B for each of these. How many total ways is that?
8.
Everybody good? All right. So there's 8 ways that could happen. That's by far, by the way, the most common one. What's another sample I could get besides 2, 5, and 9? So I heard 2 different things. So 2, 2, 5. And how many ways can 2, 2, 5 happen? There's only one way to get 2 2s, right?
Yeah, so it doesn't matter which order you have them in.
Correct.
Okay.
Right? So really, you'd get the 2 2s, and then
You either have 5A or 5B.
5A or 5B. So there's 2 ways that one can happen. Are we all comfortable with how this is going? Okay. So 2 ways. Okay. And so we have 2, 2, 5, 2, 2, 9, same idea. And then let's see. 2, 5, 5. And 5, 5, 9. And 5, 9, 9. And 2, 9, 9. Is this all? Is that it? Is everybody good? And I have these 3 samples, right? Or I have these samples of 3. Okay. All right. Now, here's what we're going to do next. We're going to kind of split up this, all right? If I have, if my sample is the 5, 5, 9, can I calculate the X bar for this sample? The mean of this sample of 3. How would we find the mean of these 3 numbers?
Same way as you find.
Yeah. So if I wanted to find this mean, I would do 5 plus 5 plus 9 divided by 3. And in fact, that sample has a mean of 6.33. $19 divided by 3 is 6 1/3. Okay. Is everybody with me? Okay. What I need us to do is find the mean of each sample. But I don't think that we each need to do every sample. You guys get what I'm saying here? So maybe these guys over here, can you guys find these means? And then center aisle here, can you find these means? And then windows, can you find those 2? And I already found that other one. Did you guys catch my drift here? so that not everybody's finding a gajillion means. So when it was 259, what did you guys get for the mean? 5.33. Okay. And for the 225? Okay, and then you guys for the 229, what did you get?
4.33.
And 4? Okay. Okay, and then we had 6.33.
For 225, I actually did 2 plus 2 plus 5 divided by 3. So all together.
Oh, got it. So that should be 3. I thought that felt kind of high. All right. And then what were the two means that you guys found?
7.66.
All right. All right. So the next thing we're going to do is build a histogram. Okay. So the x-axis would be our possible sample means and the frequency. And you guys, what I'm going to do is I'm going to kind of make my first bar go to 4. So what is the frequency? Oh, wait, I lied. 3, because we have a 3. And then this will be 4. This will be 5. This will be 6, 7, 8. All right, so as we build these, y'all, okay? When for the bar for 3, we want to say how many of our means are in between essentially 2.5 and 3.5. Is everybody with me? And looking at our frequency table, how many are between 2.5 and 3.5? Let's see. This one is, right? Anything else between 2.5 and 3.5? So my frequency for that bar will be 2. All right, and then the next bar, how many are between 3.5 and 4.5? Let's see. That would be this one and this one, yeah? So that one's going to go up to 4. What about between 4.5 and 5.5? Huh? Ooh. Between 4.5 and 5.5?
8.
8? Yeah? That's this one? Are we good? Five and a half and 6.5?
4.
4? 6.5 and 7.5, technically 0, and then 2. Because it's 7.67, yeah? Wait, yeah. We getting the basic premise of this?
Why is it
Wait.
4 for this?
I think this one
There's only 2.
yeah. This one's 4 and this one's 1, give or take. Wait,
Why, it should be 2 and 2.
yeah. 2, 2, 2. Kind of like that. All right, so here's what I need someone to do next, just one person. Can you put the sample means into your L1 and the frequencies into your L2 and find the mean and standard deviation of this new graph?
And then 1.28.
All right, so I want to make sure we're kind of understanding something that's going on here. On this histogram is practically a dot plot. Okay, like we can think of them the same. And so essentially we had 2 sample means that were a 3, we had 2 sample means that were a 4, 2 that were a 4.33. That's like 8 that were at 5.33, etc. Do you guys kind of see what's going on there? Okay, all right. And if I asked you to like kind of look at the shape of that, it's starting pretty mound shaped, pretty symmetric, not quite perfect. Okay, so even though the population from which we were sampling was uniform, okay, the shape of those means, those different means that we got based off of each sample, were approaching normal. I wouldn't call them normal, but they're definitely getting more mound shaped, more symmetric. Okay? So, the concept of we take a sample, we measure it, put it back. Take a sample, measure it, put it back. This is all the different ways that could happen for this population. Every single possible sample and the probability that it happens. Okay? All right? And that... So like in our world right now, we're going to know a ton about our population from which we're sampling, and then we're going to take a sample and make conclusions about that sample, okay? Like, is this a weird sample? Is this unlikely? Something like that. Next units, what we do is we don't know anything about the population. We only take the sample and we try to make conclusions about the population. All right? Now, it's important for us to understand some other really important ideas here, okay? So in this next piece, we're going to talk about something called the central limit theorem, okay? And to kind of talk that through, I'm going to start with a population. This is movie budgets. I feel like if I'm remembering correctly, it's movie budgets from the year 2017. It's either 2017 or 2018. I can't quite remember. Is anybody shocked to see the shape of this distribution of movie budgets? Most of them, not bad. And then you have your blockbusters that cost a ton of money to make. But there's not a ton that happen that. And a lot of like budgetary income, all those things typically have this strongly skewed right shape. But are you guys comfortable saying the shape is very much skewed to the right? Strongly skewed right. And you can kind of see some summary statistics about our population. The population mean, the summary of the mean is 51.379. The standard deviation is 57.927. All right. So the first thing I did using this website that I have is I took 3 samples, each were size 10. So in other words, for each of these samples, though it might be hard to see because it's hard to see the stacked dots, there are 10 different movie budgets that were drawn out of here. Is everybody good? So like as you look at these 3 samples, you like this one has a mean of 108, this one has a mean of 28.5, this one has a mean of 70. Everybody good? How do the samples compare to each other? Are they close? I'd argue they are not very close at all. Okay. But we could make a graph that is the means from these samples. And so far, if I were to do that, I'd have, let's see, I'd have, here might be the 28.51. Here might be the 70.4. Here might be the 108. Could I then take a different sample of 10 and calculate the mean of a different sample?
Yeah.
Yeah. Is it going to be any of these numbers? No. Okay. Now, before we get too much further, why is this one such a high sample mean?
Because you have an outlier.
An outlier here, probably.
Oh, you have a lot of outliers.
Yeah. Big picture, go back to my population. This isn't a typical sample, right? I would not call this a representative sample. Does that mean there was something flawed in the process? No. Okay. In fact, the process to gather each of these samples was the same. But when my sample size is 10, it's not that crazy to get a sample like this one. Is everybody with me? This one looks at least a little bit closer to the population, right? And its mean is a little bit closer to our population mean. This one doesn't have any of the big movies, really. Like, I would call that big budget one not one of the super high ones. You get what I'm saying here? Is everybody good? All right. And so we're thinking about, like, what will the possible samples look like? Okay. Now, imagine I had 1,000 of graphs like this one, and I plotted the mean of every single one of them, like we were starting to do here. Okay? That's what this graph is at the bottom. So that 108 is probably this guy right here. And the 28.51 is probably this guy right about here. So each dot on here is a mean of a sample. Is everybody good? All right. And these were all right. And now, this is what we would call a sampling distribution. And I'm going to just kind of say, this is of the sample mean. We're going to learn several sampling distributions throughout the course. This is the only one that's going to be in Unit 6. Okay? All right. Next, instead, what I did is I did a very similar process, but this time, the size of the samples I took was 100. So instead of having 10 points in this graph, there are 100 points in this graph. Is everybody with me? And 100 points in this graph, and 100 points in this graph. And as you're looking at these graphs, how do the samples compare to each other?
They're all close.
I would argue that these are all pretty similar. And not only that, what shape do they have? What is the shape of each sample? Skewed right. Very much this. Are you guys with me that the samples themselves resemble our population? Like, we're not getting that one that has, like, super more huge values than it should. When the sample size was 10, it was reasonable to get one that had maybe, like, an overabundance of those big budget movies. But when the sample size is 100, you're not getting 100 big budget movies. You're going to get a more balanced, more representative sample. Okay? And now, if we started to graph these means, $45.421, 52, 54, they're a lot closer together. Is everybody with me? And imagine I took a whole bunch of these samples. I took another one of these. Would you guys feel better saying that that mean is going to be somewhere between 45 and 55? That feels about right? Like my means are going to be less spread out. Okay. And in fact, when the sample size was 100, even though my population was skewed right and each individual sample was skewed right, the means are still approximately normal. Okay? So, these three graphs were done by taking samples from the same population. The only difference is these ones, the sample size was 10. These ones, the sample size was 50. These ones, the sample size was 100. Okay? All right. So, as we take larger sample size, as n increases, the shape gets closer to normal. The mean of the sampling distribution gets closer to the population mean. Now, lastly, the spread. I want to show you this kind of in two ways. You can see it has up here it says the number of samples that are on the graph, the mean, and then it says something called standard error. Standard error just means the standard deviation of one of these new things called a sampling distribution. Okay? So what do you notice about the standard deviation as the sample size increases? So small sample, this is my standard deviation.
It's smaller.
Yeah, the standard deviation decreases. So the other way I can see that, you guys, this scale goes from about 20 to 120. This one goes from about 35 to 75. This one goes from about 40 to 65. Do you guys see? This is on a much smaller scale. Okay, so all of this goes with something we call the central limit theorem. That says as n increases, sampling distributions get closer to normal. And in fact, we are allowed to say that no matter what we know about our population, if the sample size is large enough, we're allowed to assume the sampling distribution will be normal. And for right now, that normality rule is you want your sample to be large enough. And the definition of large enough is if your sample size will be greater than or equal to 30. Always 30. All right, so I want to introduce some quick kind of notation. So we have mu, this symbol mu, that's the one, like when you do the normal distribution in your calculator, this is the symbol your calculator is trying to do in a pixelated way. Okay, mu is the mean of a population. And likewise, we have sigma, which I didn't put here for some reason, is the standard deviation of a population. Okay, these are describing individuals. Okay. We also have the mean of x bar. This is the mean of the sample means. And likewise, sigma of x bar is the standard deviation of sample means. And for what we're going to be doing in Unit 6, okay, you will know these will be known, and we're going to find probabilities that certain samples can occur, okay? When we get to Unit 7, we'll know the sample, we won't know the population. That's the big crux of what we do. Okay, so lastly, turns out that the value for the mean of x bar is equivalent to the value of the mean, population mean. This is very intuitive and not intuitive all at the same time. Okay? You guys, imagine we had packages of fun-size M&Ms. They're all supposed to be 2 ounces. Okay? Everybody good? And let's go ahead and say that, I give you guys each a sample of 2-ounce packages of M&Ms. Are any of you going to have 2 ounces? Maybe. You might have 2 ounces of M&Ms, right? Is it guaranteed? No. However, if you know that the actual average of those ounces is 2 ounces, would you guys be comfortable saying that overall, if we took an average for you guys, that would be pretty darn close to 2 ounces? That the averages are going to be close to the population value, even though the individuals are not? Mm-hmm. That's all this is saying. The mean of the averages should equal the mean of the population, right? Okay? These two things mean different things, because this is the mean of the averages, this is the mean of the individuals, but it's like, there should be pretty darn close to each other. The standard deviation of the x bars should go down. That central limit theorem says it's going to go down based on how big your sample is. So how much does it go down? You divide by the square root of your sample size. So let's look at an example. The average 6th grader can read 10 words per minute with a standard deviation of 11 words per minute. I'm going to take a random sample of 66th graders. Okay. If my sample size is 60, are you guys comfortable saying my sample size is bigger than 30? So here's what I can say about my sample means. They will be approximately normal. The mean of those sample means is going to be 10, because it's going to be the mean of my individuals. The standard deviation of my sample means is going to be smaller. It's going to be 11 divided by the square root of 60.
1.42.
Everybody good so far? All right. Now, this is going to show up in your homework. like it happened, it was just like the first question someone brought me yesterday in second period, okay? The question here is saying, what is the probability that we find a sample of 60 sixth graders whose mean is more than 11? So like when I read that, okay, the first thing that jumps to my brain is that word. I'm not finding the probability an individual sample or an individual sixth grader is reading more than 11 words per minute. I'm finding the probability that a sample mean is greater than 11. And if that's the case, I want to compare that sample mean not to the numbers here. I want to compare it to the ones that describe the sample means, which is why we would do this part in the first place. Okay? So, if I'm finding the probability that x bar is greater than 11, my picture is going to use the standard deviation of x bars. And so the only difference in terms of what that looks like in the calculator is now my standard deviation needs to be divided by that square root of my sample size. After that, how do I answer this? This picture looks awfully familiar. This is a picture we can throw into that normal CDF in our calculator.
Why do we know it's a normal CDF? Is it always normal CDF when it's these graphs?
If it's normal, you use either normal CDF or inverse norm.
Okay. How do you know if it's inverse normal or CDF?
Do you know the boundaries or do you know the area?
Okay.
What are we getting?
0.241.
241. Everybody agree?
What did you enter in?
So your lower would be 11.
Yeah.
Your upper would be a gajillion, just some really big number.
Uh-huh.
Your mean would be 10. Your standard deviation would be 11 divided by the square root of 60.
Got it.
Or if you used 1.42, because we found that above, that would be fine. So when it says mean, that standard deviation can't be the standard deviation of the individuals. It has to be the standard deviation of the samples. That's really what it boils down to. Everybody good? All right, we got one more example in the back here. Let's talk about the shape. My sample size is 35, which is pretty darn big, right? So we've got approximately normal. What is the mean of my samples going to be? The mean of my sample means 27.4, and the standard deviations of those sample means will be 5 divided by the square root of 35, which is 0.845. All right. This thing's dying every 30 minutes now. Was it probably we find a sample of 66? Oh, you guys, this is definitely that I copied and pasted the last problem and forgot to change part B. Definitely true. Let's go ahead and say, what is the probability we get a sample of 35 students whose average age is younger than 25. Again, as soon as you see that word average, we're finding the probability that X bar. And what would we say about the sample mean if it is younger than 25? Younger would be less than 25. And again, we're talking about X bars, so we're going to use the 27.4. And our standard deviation, we're going to use that 0.845, not the standard deviation of individuals. We use the standard deviation of the X bars. And then, I don't know, 25 would be here, shaded less than. Before, I want to tell you guys, like, I know already that this answer is going to be a low probability. How do I know this is going to be low?
Because the 25 is going 30. Or
The 25, you guys, look at my standard deviation.
It's more than 2.
It's more than 2 standard deviations below the mean, right? So this is a pretty unusual thing to happen. Is everybody good? Like, because as you start doing plug and chug in the calculator, sometimes it's hard to make sure your answer makes sense. Like, kind of thinking through as I plot a value, how many standard deviations is that is kind of helpful. Everybody okay? Is it small?
0.002.
I mean, that feels like a reasonably low, like reasonable for this, because for how many standard deviations from the mean it is.
where'd you get the 0.845?
Because that was the standard deviation of the X bars that we found up top. You could easily type this. The trick is recognizing that if it's asking for a mean, your standard deviation you need to include divided by that square root of the sample size. Okay, from here, y'all. You guys have Lab 6A. It is due tomorrow. Correct. Okay. The plan for tomorrow is Lab 6B, homework number 6. Those are due essentially Monday. Okay?
Before the test.
They're due before you take the test. That's reasonable, yes? Okay. In terms of work you have to do, this is it. My plan over the next 2 days for you guys is to do whatever you ask me to do. If you want to work on this stuff, you can work on this stuff. If you want me to come up with practice questions similar to what's on the test, I'll come up with practice questions that are similar to what's on the test. Does everybody know where to find the topics that are on said test? Okay. They are up on Blackboard in the announcements on Blackboard. They will be up on Blackboard through the end of the day on Tuesday. Then I have time just to go away on Tuesday. They're up until you take the test, okay? I'm not kidding when I say if there is something on that list that you don't know how to do, it is fine if you don't know how to do it right now. It is not fine if you do nothing about that between now and Monday. Do you guys get what I'm saying? You got to be like, and my advice to you is not to be like, oh, just treat the next few days as work days. I think you should work outside of class so that you can ask me whatever it is you need to ask me tomorrow and Friday, right? Okay? Because I made that list, literally, you'll see problem 1 says finding empirical probabilities, and I give you raw data, and I say find an empirical probability, because that's what it is. I made that list going page by page on the test. Does everybody understand what I'm saying here? Okay. What do you need from me right now? Perfect. Have fun.